This topic will introduce the idea of a binary operation and will look at properties such as commutativity, associativity, identities and inverses. We will work with a range of different binary operations, including modular arithmetic. A binary operation is one that takes two elements from a particular set and performs an operation on them to give an output. Any symbol can be used to represent a binary operation, and this symbol is usually defined at the beginning of the question. So some examples of binary operations would be, for example, the binary operation represented by this symbol could be that A operation B involves adding A to B, and this could be applied to the set of numbers A and B in the real numbers. So any two real numbers could be added in this way. Another example may be represented by this symbol here. A operation B could involve squaring A, cubing B, adding them together, and this could apply to any A and B in the natural numbers. Here are a number of questions involving various binary operations that are defined in the question. Pause the slide now, work through the answers before continuing. So the answer to question 1, 3 operation 5 using the operation above would equal 4. Given that A operation B is 0, the relationship would be as follows. A minus B squared would need to equal 0, which would be true only if A equaled B. For question 3, the possible pairings x and y, such that x operation y would not be in the set of numbers, so would not give an answer 1, 2 or 3, will be the pairs x is 1, y is 2, x is 1, y is 3, x is 3, y is 1, and x is 3, y is 2. And for question 4, using the operation on matrices given here, the answer would be the following matrix. Considering the set of positive integers, which of the following would be binary operations for two elements x and y? And the answer is that all of them would be binary operations apart from D, which only has one input value, whereas a binary operation must have two inputs, and F, which has 3 input values, so again would not be a binary operation. We're now going to introduce the concept of modular arithmetic. So imagine that it's 10 o'clock. What time would it be in 5 hours if we were working in the 12-hour clock? So adding 5 hours onto 10 o'clock would bring us to 3 o'clock. So what has happened here is that we've looped around in groups of 12 and then gone back to the start. So this idea is linked to the topic of modular arithmetic. So in this case, what we are doing is calculating modulo 12, sometimes shortened to mod 12. So we could write it as 10 plus 5 is 3 mod 12. So generally speaking, the notation would be that A equals B mod n. A, B and n would all need to be integers for this to work. Another way of looking at it is to say that if A and B were both divided by n, they would have the same remainder as each other, which is why they are equal mod n. Now pause the slide and answer each of these questions here. You're trying to work out the values of x in each modulo as given in the question. One way to calculate these can be thought of by dividing by whatever the number is. So for example, question 1, if you're trying to work out 37 mod 6, you could divide by 6 and see what the remainder is. The answer will need to be between 0 and 5 for question 1. Another way of doing it is to keep subtracting multiples of 6 until you are in the range from 0 to 5. So in other words, until you cannot take away multiples of 6 anymore. For some of the more complicated ones, you may need to add multiples of whatever n is. You may need to use some trial and error for some of the later ones as well. So here are the answers to each of the 8 questions for question 1, question 2, question 3, question 4, question 5, question 6, question 7, and question 8. So you'll notice that in each case, if we're working mod n, the answer is always between 0 and n minus 1. For each of these calculations, we are going to first of all work out the sum or the product of the two numbers, and then work out what the answer is mod n in each case, so whatever the modulo is given. So the first question, we get 51, which is reduced to 3 when working mod 6. The next one we get 62, which is 7 when working mod 11. The third one, we get 105. Because this is in the 5 times table, 105 will be 0, mod 5. Next question gives us 518, which is 2 mod 6. The next question, 925, which is 1 mod 11. And finally, 2294, which gives us 4 when working mod 5. We're now going to do the same calculations again, but this time we are going to work out each of the values mod n first and then find the sum and the product afterwards. So for the first question, reducing the numbers first, we get 1 plus 2, which also gives us the answer 3 mod 6. The next question, get 3 plus 4, which is 7 mod 11. The next question, we get 4 plus 1, which is 5, but because we were working mod 5, we need to take away 5, so we end up with an answer of 0 mod 5. The next one, we get 1 times 2, which is 2 mod 6. And for the next one, we get 3 times 4, which is 12. Because we were working mod 11, this reduces to 1 mod 11. And finally, 4 mod 5. So we can see that the answer is the same whether we reduce mod n first or whether we do the calculation first and then reduce mod n afterwards. So the notation for a plus b when working mod n is to write a plus with a subscript of n, b. And the notation for a multiplied by b mod n can be written as a, then a multiplication sign with a subscript of n, b. The reduction mod n can either be done before working out the sum or the product or after. It will give the same answer either way. So an example of this is that if we were to calculate 37 times 14 mod 6, we would get 518, which is 2 mod 6. Or we could reduce 37 and 14 first to give us 1 times 2 mod 6, which also gives the answer of 2. So we're going to use this fact to prove the result above. This fact tells us that if we're working mod n, then a number a can be written as some integer multiplied by n plus a remainder. So R1 there, that is the number a when reduced mod n. B can similarly be written as a different multiple of n plus another remainder. So in this case, R2 is the number b when reduced mod n. We're going to use this notation to prove the result that the sum and the product can either be done before or after reducing mod n. So we're going to use this notation to show that A and B can be either reduced mod n first before adding them together, or the result can be reduced mod n afterwards and it will give the same answer. So if we were to find the sum first, mod n, we could say that A plus B mod n can be written as seen. We can then regroup this, putting the multiples of n together and factorising out multiple of n, and then the two remainders together at the end. Now, because we are working mod n, any multiple of n will be 0, so n times p plus q will equal 0. That will leave us with the answer r1 plus r2 mod n. If we were to do the same calculation but find the sum after reducing mod n, then adding these two together would just involve adding r1 and r2, because by reducing mod n first, pn and qn would already equal 0, leaving us with the same answer as above. We can also do the same calculation but with multiplication, finding the product of a and b. So by finding the product of a and b first, we find that a multiplied by b mod n gives us the following expansion: pqn squared plus pnr2 plus qnr1 plus r1r2. Again, we can factorise out a multiple of n from the first three terms, and we know that any value when reduced mod n, any multiple of n will be 0. So this entire term at the beginning will equal 0, leaving us with just the product r1, r2. If we were to start with a and b first and reduce them mod n before finding the product, then a would just be r1 and b would just be r2, leaving us simply with the same answer, r1, r2 mod n. Another definition, the inputs for a binary operation usually come from the same set, and we say that this set is closed if the outputs also fall within this set. So for any two inputs, when the binary operation is performed, if the answer is also in that same set, we call it a closed set under that binary operation. It's not necessary to be able to achieve every single element as the output, but any output that can be achieved needs to belong to the original set in order for the operation to be closed. So if we were to consider only the set of positive integers, which of the following operations, addition, subtraction, multiplication or division, will be closed? In other words, when we perform these operations, which ones will only give us a positive integer as the answer? Pause the slide briefly to consider this. So the first one, addition. If we were to add a positive integer to another positive integer, the answer would also be a positive integer. So we can say that addition is closed on the set of positive integers. However, subtraction, subtracting a positive integer from another positive integer, could give 0 or a negative integer, for example 2 minus 5. So subtraction would be not closed. Multiplication, multiplying two positive integers together, will always give a positive integer as the output, so multiplication is closed on the set of positive integers. Division will not always give an integer. Sometimes doing a positive integer divided by another positive integer may give a fraction, for example 2 divided by 5. So division would not be closed on this set. The set that a binary operation works on does not need to be a set of numbers. It could be a set of objects instead. So we're going to define a set of polygons whose edges all have a length of 1 unit. So a set of polygons with n edges will be denoted using the notation n in triangular brackets. So for example, if n was 4 here, it would be the set of all polygons with 4 edges that all had a length of 1. An operation here is defined as taking two polygons and joining them along one of the edges, which will match exactly because all of the edges are of length 1, to form another polygon. So pause the slide and consider what each of these answers would be. So in part A, we want to know what would be the answer to this binary operation. This is the set of polygons with 3 sides, the set of polygons with 4 sides. If we were to take polygons from each set and combine them in such a way, we would actually end up with a polygon with 5 sides. This is because in joining together two such polygons, 2 of the edges, 1 edge from each polygon, becomes an internal edge to the shape, so it's no longer an edge. So there would always be, in this case, 5 external edges left. So in general, for x and y, what would happen is that the new polygon would have x plus y and then minus 2 edges. So this new set would be x plus y minus 2. Is this binary operation closed on this set? The answer is yes, because taking any 2 polygons in such a way and combining them will always give another polygon. So if the set we are considering is any polygon with n edges for any value of n, then it will always be closed because the answer will always be another polygon with edges of length 1. Next, we're going to consider the set M, which consists of all matrices of the form K001, where K is any real number. So first we want to consider whether matrix addition would be closed on this set, and secondly whether matrix multiplication will be closed on this set. Pause the slide to consider the questions. So in order to answer part A, we could start by taking 2 general matrices from this set. In this case, we're taking K001 and M001 for 2 different numbers, K and M. And we can see that when we add these together, the matrix that is given as an output is not within the set. It does not follow the form to be in set M because the bottom right element is 2. So the answer is no, matrix addition is not closed on this set. However, matrix multiplication, when multiplying K001 and M001, gives us the matrix KM001. And because K and M are real numbers, therefore Km will also be a real number. The output for this operation will be in the set M. So this will occur for any such real numbers K and M, so we can say that yes, the operation of multiplication is closed on this set. Next, we are going to define the property of a binary operation being commutative. Now we say that a binary operation is commutative if for all elements A and B within the set that the binary operation is working on, A operation B gives the same answer as B operation A. If this is not true for all values of A and B, we would say it was not commutative. In order to show that something is commutative, we would need to prove that this worked for all values of A and B within the set. However, to prove that something was not commutative, we would only need one example of a pair A and B that did not work in order to show this was the case. So for each of the 5 questions below, decide whether or not the binary operation is commutative on the set given. If it is not commutative, find a counterexample to disprove the commutativity. So question 1, the binary operation is addition for real numbers. We know that addition is commutative. We know that for any 2 real numbers, if we add A and B or B and A, the answer will be the same. Next, 2A plus B. So we are going to consider whether this would be the case. Essentially, we are working out for any values of a and b, would 2a plus b be the same as 2b plus a? In other words, would interchanging a and b in the rule give the same answer? And it's fairly straightforward to find a counterexample. If we use a equals 3 and b equals 4, we can see that 2 times 3 plus 4 does not give the same answer as 2 times 4 plus 3. So we've proven that this is not commutative. For the third example, this is commutative. We can see that x squared plus y squared plus 2xy will be commutative, interchanging the x's and the y's. This can be shown algebraically. X squared plus y squared would be the same as y squared plus x squared, so interchanging x and y here. 2xy, because multiplication is commutative as well, interchanging x and y would give the same answer. The fourth one, matrix multiplication on two square matrices, A and B. We know that matrix multiplication is not commutative, and we can find a counterexample fairly easily just by choosing two matrices, multiplying them in reverse order and showing that the output is not the same. And then finally, x operation y is 1 over x minus 1 over y plus 1 over xy for integers x and y. We can find an example here. If we let x be 2 and y be 3, we can see that interchanging the x's and the y's in the question will not give the same answer. We are now going to prove that multiplication of matrices of the form k001 for a real number k is commutative. So we're going to do this by taking two matrices that would be in that form, multiply them in either order, and show that the answer is algebraically the same. So we're going to take k001 and m001, multiplying them either way around. We get km001 and mk001. And because we know that multiplication of real numbers is commutative, we know that km and mk is the same answer. So therefore, matrix multiplication of this particular form is commutative, even though generally speaking, matrix multiplication is not commutative. So the next definition is associativity. A binary operation is said to be associative on a given set if for all elements A, B and C in that set, if the answer is the same, whether A operation, B operation, C is calculated either with the brackets around the A and the B, so calculating that part first, or with the brackets around the B and the C, calculating that part first. If the answers are not the same for any values A, B and C, then that one counterexample is enough to prove that it is not associative. However, to show that something is associative, you would need to show that the result is always the same for any values A, B and C in that set. So we're going to find for each of these binary operations, we're going to calculate A operation, B operation, C both ways, and we're going to determine whether they are associative or not. If they're not associative, find one counterexample. If they are associative, you would need to show algebraically that this was the case. So I'm just going to write out what you're going to be finding here. So for the first one, A operation B is A plus B. You are determining whether A plus B plus C, whether that is the same as A plus B plus C. The second one is slightly more complicated. For this one, because the operation is 2A plus B, we are trying to calculate A operation B operation C, which would be this. That would be, so A operation B in brackets will be 2A plus B. Then this answer here, we are performing the operation with C. So in other words, we are going to be multiplying this answer by 2 and then adding on C. So we're going to be finding 2 lots of that plus C. We want to know, is that the same as if you were to do A operation, B operation C with the brackets around BC. So to find that, B operation C would be 2B plus C, and you're doing A operation with that answer. So in other words, it will be 2 lots of A plus 2B plus C. For the third one, we've got X operation Y is X squared plus Y squared. So if we were to do X operation Y operation Z, so or A, B and C, doesn't matter which ones we use here. If we were to put the brackets around the X and the Y, this would first of all involve finding X squared plus Y squared. We would then be performing that operation with Z, so we would square this answer and add Z squared, and we are trying to decide whether that is the same as X operation Y operation Z, where the brackets go around the Y and Z. This would be Y squared plus Z squared. We would then be calculating the answer of X operation, the answer from Y operation Z. So this would be X squared plus the bracket squared. For the fourth one, we are determining whether for 3 matrices A, B and C, would we get the same answer if we calculated AB first as if we were to calculate BC first. Be careful not to change the order with these, as matrix multiplication is not always commutative. And finally, for the last one, we are going to calculate X operation Y operation Z, first of all by putting the brackets around the X and the Y. So that would be X operation Y would be 1 over X plus 1 over Y. We're then going to perform the operation, this answer operation with Z. So in other words, 1 over this answer plus 1 over Z. We want to know, would this be the same as calculating the other way around? So this would be X operation Y operation Z with the brackets around the Y and the Z. So this would give us 1 over Y plus 1 over Z as the brackets. We would then do 1 over X plus 1 over the answer from there. We want to know, are they the same thing? So pause the slide now and determine, either by a counterexample or by algebraic proof that it works for all A, B, C or X, Y and Z, whether or not this is associative. So the answers to each of these, well, the first one, it's fairly straightforward to see that A plus B plus C would work regardless of where the brackets were. So the first one is associative. For the second one, we can see that this is not always the case. We could find a counterexample, just choosing 3 values of A, B and C, such that this doesn't work. Any 3 values would work, but choose specific numerical examples as a counterexample, not just general algebra. We would find that this is not associative. For the third one, again, just carefully choosing a value of X, Y and Z such that this does not work. We will end up with a non-associative binary operation. Now we can calculate using matrices here. Now we actually know from matrix multiplication that matrix multiplication is associative. So although this is quite a long-winded way of calculating, we can often just use the associativity property of matrix multiplication to say that yes, this would be true. And for number 5, finding some counter examples, we would find that this does not give the same answer either way around, so just choose any value for x, y and z such that it doesn't work and conclude that it is not associative. I'm now going to return to the set we looked at earlier of polygons with edge length unit 1, and we're going to prove that the operation of combining 2 polygons together along an edge, prove that that is associative. So the proof is as follows. If we were to first of all do x operation y, this would leave us with x plus y minus 2, operation with z. If we were then to do this, we would then be adding together these 2 numbers and subtracting 2. So we would end up with x plus y plus z minus 4. If we were to go the other way around, y operation z would give us y plus z minus 2. If we were then to do x operation, this answer here, we would get x plus y plus z minus 4. So we can see that both ways round we get the same set, so the operation is associative. Our next definition is the identity for a binary operation. So the identity for a particular binary operation, we often use the letter E for this. The identity basically leaves any element unchanged when the binary operation is calculated in either order. So for example, if E operation x would always give the answer x, and if x operation E would always give the answer x for every single value of x in that set, then we could say that E was the identity for that set. So the identity element is unique to a binary operation. In other words, there would only be one E that would work for each binary operation. A set would not have more than one identity. Not all binary operations have an identity. Also, the identity needs to be the same identity for any x value. It cannot, we cannot have different identity elements for different elements. It has to be the same value for the entire set. For each of the following binary operations, decide whether or not there is an identity element. If it exists, state what it is. So in the first one, an identity element E would need to satisfy the following. E plus B would need to equal B. This would happen if E equaled 0. And similarly, A plus E would need to equal A. Again, this would be satisfied by E equals 0. So the identity element is 0. For the second one, we would either need 2E times B to equal B, which would result in E being a half, or we would need 2A times E to equal A. This would also give E equals a half. So a half is the identity element for this operation. For the third operation, an identity element E would need to satisfy 2E plus 2B equals B. This would result in E being minus B over 2. Now, because B is an element in the set, this would not be unique because every element would need a different value of E in order for this to work. So there would be no identity element for this binary operation because there would not be a unique value of E that worked for every element. For the fourth, we would need a matrix such that E times B gave us matrix B. So the identity element would work in that, unsurprisingly. And also A times a matrix E would need to give us the matrix A. Again, the identity element matrix. So the matrix 1, 0, 0, 1 would be the identity element for the set of matrices. For the next step, we would need the 0 vector, so a 3x1 matrix with elements 0, 0 and 0. This would work for any matrix in the set of 3x1 matrices. So the vector 0, 0, 0 would be the identity in this case. Finally, x plus y plus 1 mod 2 in the set 0 or 1. So this binary operation is only defined for the set of numbers 0 and 1. So e plus y plus 1, when calculating mod 2, would need to equal y. E equals 1 would satisfy this. This can actually be found by trial and error, just because there are only 2 elements in the set to begin with. Similarly, x plus e plus 1 mod 2 would need to equal x. E equals 1 would also satisfy this. So just by trial and error, we can see here that 1 would be an identity element for both elements in this set. Our next definition is an inverse of an element. This is written as the elements to the power minus 1. So the inverse of x will be written as x to the minus 1. And for any element, if it was multiplied using the binary operation by its inverse in either order, either x operation x inverse or x inverse operation x, the answer would need to be the identity element for that set. An element will be self-inverse if, when multiplying it by itself under the binary operation, would always give the identity element. In this case, this would mean that x also equaled x inverse. For each of the following binary operations, the identity element has already been given. Find the inverse of the element given in each question. So for question 1, the identity element has been given as 0. So the inverse of a, which is 4, would be minus 4. So that 4 plus minus 4 gives an answer of 0. For the second one, the identity element has been given as a half. We want to find the inverse of x equals 8. So the inverse will be 1 over 32, so that when 8 and 1 over 32 have the operation performed on them, the answer is a half. For the third one, we can actually use the formula for inverse matrices for this one, because we know the identity element of a 2 by 2 can be found, it is 1, 0, 0, 1, so we can use the inverse formula. The inverse is given there. For number 4, this is matrix addition, so we know the identity element is the 0 matrix, 0, 0, 0, 0. So the inverse of A, B, C, D would be minus A minus B minus C minus D, because those two add together to give the 0 matrix. And finally, for number 5, the identity element is minus 1. So in order to get the inverse of A, we would need minus 2 minus A for the particular given value of A. Now complete the selected questions from the binary operations exercises, exercise 1, exercise 2 and exercise 3.